Hello, good morning to everyone. Myself, Dr. Mahadev Unde, Professor in Electrical Engineering, Jheel College of Engineering and Research, Pune. In a previous video lecture, we have learned the synchronous impedance method of finding the voltage regulation of the alternator. In this problem, we are going to solve the numerical based on it. Let us consider the numerical based on it, which was asked in SPPU examination in November 2012. A 10 kVA, 440 volt 50 Hz star connected alternator has open circuit characteristics given below. The feed current 1.5, 3, 5, 8, 11 and corresponding open circuit voltages line to lines are given. Now the rating of the alternator is 440 volt and correspond to 440 volt the feed current required is 5 ampere. Okay. Then we have converted the line to line voltage to the per phase voltage dividing it by root 3. So the open circuit voltages per phase are tabulated in the third row. Okay. Then what is given, a feed current of 4 ampere is required to circulate. Full load short circuit current, assume that the armature resistance is negligible. Determine the full load voltage regulation at power factor 0.8 lag, 0.8 lead and unity power factor. Okay, now try to understand the meaning of this 4 ampere. A feed current of 4 ampere is required to circulate full load short circuit current of short circuit current. So it is necessary to find out what is the full load current, and this full load current equal to short circuit current. So at this feed current 4 ampere, what is the open circuit EMF per phase or from OCC. So from the given characteristics, let us plot the open circuit characteristics as shown. See here the same parameters I have repeated here, and here we have to take the proper scale for the short circuit test. Feed current equal to 4 ampere and that is correspond to ISC equal to IFL. Okay, and the scale taken, the x-axis 1 centimeter equal to 1 ampere and y-axis 1 centimeter equal to 25 volt, that is 1 mm equal to 2.5 volt. So accordingly, this OCC has been plotted. OCC has been obtained. See, OCC, this is the open circuit characteristics. Okay, this is the open circuit characteristics shown in the figure, and on the x-axis feed current is taken, on the y-axis open circuit voltage per phase is taken. Okay, the same graph which has been used for the Pottier method can be used for the synchronous impedance method as well for the MMF method. Okay, now here the short circuit characteristics are not directly given, but it is given that when the feed current is 0, short circuit current is 0. When the feed current is 4 ampere, short circuit current equal to full load current. So we have to find out and join the straight line passing through the origin, that is the short circuit characteristics. Okay, so let us proceed to find the full load armature current. Okay, so IFL equal to ISC equal to 10 into 10 raised to 3 divided by root 3 into 440, and that has been asked, that is 13.12 ampere. Thus, the IF equal to 4 ampere and corresponding short circuit current is 13.12 ampere. Okay. From OCC, when IF is 4 ampere, the open circuit voltage per phase is 212.5. Let us check it. When it is 4 ampere, see, this is the line of 4 ampere. We will check it. Say this is 4 ampere and it is this much. See, each mm carries a 2.5 volt and therefore this is 200. Here it is 225. Here it is 212.5. Thus we can find out the ZS. So the synchronous impedance, we have obtained this value. The synchronous impedance Z is equal to open circuit voltage per phase divided by short circuit current per phase, both at the same feed current. Here we have obtained both at the feed current equal to 4 ampere. So Z is equal to XS, because the armature resistance is negligible, that is given. So 212.5 divided by 13.12 equal to 16.2 ohm per phase at a feed current of 4 ampere. Okay, Ra equal to 0, and therefore Z is equal to XS equal to 16.2 ohm. Now what is the voltage drop across this reactance, that is Ia XS. So 13.12 Ia multiplied by XS is 16.2, it is 212.54 volt. Now voltage regulation phi r at a full load and power factor 0.8 lagging. Now what is the formula for this? EPH equal to square root of phi pH cos phi plus IARA bracket square plus phi pH sin phi plus or minus IARA bracket square. Now this plus sign is used for the lagging power factor and minus sign is used for the leading power factor. Okay, so EPH equal to square root of phi pH 254.03 into cos phi, that is 0.8, IARA is 0 bracket square plus 254.03, that is phi pH into sin phi plus 212.54 bracket square. So EPH is 417.72 volt, which is greater than phi pH, and thus at a lagging power factor voltage regulation is positive. So the percentage voltage regulation is EPH minus phi pH upon phi pH, and that is equal to 417.72 minus phi pH is 254.03 divided by 254.03 multiplied by 100, and it has been obtained 64.43 ampere, 43%. Now this is the voltage regulation obtained by the synchronous impedance method. By this method, the values of the voltage regulation obtained are the little bit higher than the actual values, and thus this method is known as pessimistic method. Pessimistic method. Okay. Now similarly, we have to find out the voltage regulation at full load and power factor 0.8 lead. Now for the 0.8 lead, we have to use the negative sign here. Use the negative sign here, and rest of the things are same. And therefore, for the leading power factor, EPH is less than phi pH, and the answer obtained is 212.93 volt, and thus the percentage regulation is EPH minus phi pH upon phi pH multiplied by 100, and that is equal to minus 16.57%. So minus sign because of leading power factor. In a leading power factor, EPH is less than phi pH. Okay. So in this way, we have obtained the voltage regulation at a leading power factor. Similarly, let us find out the voltage regulation at full load and unity power factor. Here the formula is at a unity power factor, cos phi is equal to 1 and phi equal to 0, and therefore the sin phi equal to 0. And therefore EPH equal to square root of phi pH square plus IAXS bracket square. So it has been found that the answer is 331.22 volt. For unity power factor also, EPH is greater than phi pH, and therefore the voltage regulation is positive. But this value of EPH is less than the value which has been obtained at a lagging power factor. Okay. So the percentage regulation is EPH minus phi pH upon phi pH into 100, and it has been obtained that 30.38%. So the regulation is positive for both lagging power factor and unity power factor. However, voltage regulation at lagging power factor is greater than the voltage regulation at a unity power factor, and the voltage regulation at leading power factor may be either 0 or a negative. So in this way, we have obtained the voltage regulation at a lagging power factor, leading power factor, and unity power factor by synchronous impedance method. Let us solve the same numerical for the MMF method, and at the end we will compare the results obtained by using the Pottier method, by using synchronous impedance method, by using MMF method, and by using the Pottier method. Okay, let us start now. The same problem, I will not repeat now, but here it is. What is IF1 for the MMF method? For MMF method, IF1 is the feed current required to generate rated open circuit voltage per phase. And in this case, the rated open circuit voltage per phase is 254.03, And to generate this much voltage, the field current is required is 5 ampere. This is from this given data. From the given data, so IF1 is 5 ampere. And in the numerical itself, it is given that a field current of 4 ampere is necessary to circulate the full load current equal to short circuit current, and that is nothing but IF2. So IF2 is 4 ampere, okay, and you have to neglect the armature resistance and find out the voltage regulation at 0.8 lagging, leading, and unity power factor. Solution. Now the open circuit test and short circuit characteristics are plotted as before. The same data you have to use here. Similarly, the full load current is equal to 13.12 ampere, which we have obtained already, and therefore corresponding field current IF2 is equal to 4 ampere. That means this 4 ampere, when the field current equal to 4 ampere is circulated, is fed to the field winding, the armature winding current is full load, and that is equal to 13.12 ampere, and that is equal to ISC. So IF1, once again I will repeat, IF1 is the field current required to generate rated open circuit voltage per phase, and from OCC, the open circuit voltage per phase is 254.03, and corresponding field current IF1 equal to 5 ampere. Okay. Then the IF2 equal to field current required to circulate short circuit current per phase equal to full load current, and that is nothing but IF2 equal to 4 ampere. So in this way, we have obtained the IF1 and IF2. The next step is to find the resultant of this at a various power factor of the load and correspond to resultant field current. What is the no load EMF per phase that has to be obtained from the open circuit characteristics. Once you got that figure EPH, you can find the voltage regulation, that is EPH minus VPH upon VPH into 100. Okay, let us start now. So at a 0.8 lagging power factor, find the resultant of IF1 and IF2. So this is the phasor diagram for the lagging power factor. OA is the reference, that is the IF1. Then from point A, draw dotted vertical line. Then AB is IF2. Draw the AB lagging the vertical line by an angle phi. Join OB. OB is nothing but the field current, resultant field current. And remember that the angle between IF1 and IF2 in this case is 90 plus phi. Okay. Thus, the field current IF, resultant field current, equal to square root of IF1 square plus IF2 square minus twice IF1 IF2 into cosine of angle between them. And in this way, we have obtained the resultant field current is 8.06 ampere, and from the OCC, the corresponding no load voltage per phase is 317.5. Let us check it for the 8 ampere. See, just a minute. For this field current equal to 8 ampere, let us check it. Field current equal to 8 ampere, and it is 1300, and it is close to 325, but less than the 325, and I think that is 317.5. Okay, so the percentage voltage regulation is EPH minus VPH upon VPH into 100, and it has been obtained 25%. Okay, now similarly find out the voltage regulation at a 0.8 leading power factor. As the cos phi equal to 0.8, phi equal to 36.87, and therefore sin phi equal to 0.6. Now draw the phasor for the leading power factor. Draw the reference phasor as a IF1. OA represent IF1 as a horizontal line. Then from point A, draw dotted line, vertical dotted line. Then draw AB, that is nothing but IF2, leading the vertical line by an angle phi. Then join OB. OB is the resultant field current. And remember that here the angle between IF1 and IF2 is here 90 minus phi. Therefore, using the same formula which we have already used, the IF1 equal to resultant field current equal to square root of IF1 square plus IF2 square minus twice IF1 IF2 into cosine of angle between IF1 and IF2. And it has been obtained that the resultant field current is 4.123 ampere. And corresponding no load EMF per phase is 215 volt from OCC. Let us check it. 4.1. See, this is 4 and 4.1 means one line here. See, it is less than 225 but greater than 212 means around 215. Okay, let us check it how much here it is. 200 and okay, see here for the leading power factor it is 215 which is less than the VPH, and therefore percentage voltage regulation is negative and that is minus 15.36%. Now at a unity power factor, the phasor diagram OA is nothing but IF1 and that is horizontal. Then from point A draw IF2 perpendicular to the IF1, join OB, that is the resultant. Use the Pythagoras theorem here and find out the resultant field current, and it has been found that 6.4 ampere, and correspond to this 6.4 ampere the EPH equal to 280 volt from OCC, and therefore percentage voltage regulation is 12.19. Let us check this 6.4 and 285. 6.4 means it is close to 6.5. Yeah, it is, see here 250 to 75, then 300, it is around 285. Okay, so the corresponding open circuit EMF per phase is 285 volt, and therefore the percentage voltage regulation is 12.19%. So in this way already we have solved the same problem by using the Pottier method. So let us have a comparison of all these three methods. Here power factor oblique method. Method is synchronous impedance method, MMF method and Pottier method. 0.8 lagging power factor, unity power factor and 0.8 leading power factor. For a synchronous impedance method values are very high. 64.43, here 25 and here 26.56. This 64.43 is very high value. These results are pessimistic. The reason is the value of ZS obtained is quite large as compared to the actual one. And by using MMF method, the values which we have obtained are less than the actual one. Whereas by using the Pottier method, we get more accurate results because here we have separated the field current required to overcome the voltage drop due to the leakage reactance and field current required to overcome the effect of armature reaction drop. Okay. So here the Pottier method gives the more accurate result. For a unity power factor also, for synchronous impedance method it is 30.38, MMF method 12 this, and the Pottier method gives it 8.25. Now for a leading power factor, this result, this is quite large, this is more result than this is one, and here it is giving this. So the comment is synchronous impedance method gives higher results than the actual one, and the method is known as pessimistic one. This happens only because of higher synchronous impedance, because of the non-saturation region. Then MMF method gives results little bit less than the actual one. And whereas, because in MMF method, the whole voltage drop is assumed to be because of the armature reaction only. And in the Pottier method gives a more accurate result compared to synchronous impedance method and MMF method. It separates, Pottier method separates the field current required to overcome the voltage drop due to the leakage reactance, as well the field current required to overcome the voltage drop due to the armature reaction, that is IAXI. Okay, we will stop here. Thank you very much.